Okay, let's unpack this. I mean, imagine a huge online store maybe handling millions of transactions every single second, or, a social media site with just billions of users. When we're talking about data sets that are so vast, like just replicating them isn't even close to enough. How do these database systems actually keep everything running, without just collapsing under the load? It feels like this impossible balancing act.
Yeah, it's a huge challenge. And what's fascinating here is that to really scale up to that kind of, well, monumental data load, you have to go beyond just having multiple copies for safety. You actually need to break the data itself into distinct, more manageable sections. And that core idea, that's what we call partitioning.
So today we're taking a deep dive into this really ingenious art of partitioning. Basically, how databases smartly spread out both the data and the query workload across lots of machines. The whole goal is to avoid overwhelming any single one. And you'll discover the fundamental principles behind how systems you use every day manage their massive information piles, often without you even noticing the complexity under the hood.
And that brings up a good point right away, terminology. You might hear different words for this concept. While we'll probably stick to partitioning just for clarity because it's maybe the most established term. You'll also hear shard, like in MongoDB, Elasticsearch, Soul Cloud. Each base calls it a region. Bigtable uses tablet. Then you've got Node in Cassandra and React and vBucket in Couchbase.
Wow, okay, so lots of names.
Yeah, but they're all fundamentally describing the same thing, dividing up a big database into smaller pieces.
Right. So why is partitioning so critical? I mean, beyond just having backup copies through replication.
It really comes down to scalability. Pure and simple. We're talking about taking a massive data set and spreading it across many different physical disks. And just as importantly, spreading the query load, the actual work, across lots of processors. This is especially key in what we call shared nothing clusters.
Shared nothing, meaning each machine is pretty independent.
Exactly. Each machine, or node, has its own dedicated memory, its own storage. They don't share those critical resources. This avoids bottlenecks you'd get with shared resources and lets each node handle queries for its slice of the data totally independently.
Okay, that sounds super modern, very cloud native almost, but how far back does this idea actually go? Is it a new thing?
You know, it's surprisingly old. It might feel really current with all the NoSQL systems and cloud databases popping up, but partition databases, they were actually pioneered way back in the 1980s.
Yeah.
Yeah, by products like Teradata and Tandem Nonstop SQL. It's a really fundamental concept. And it applies whether you're dealing with like high volume transactions, think at online store processing purchases, or heavy analytical workloads like a data warehouse crunching huge reports. Same core idea.
Okay, so one of the biggest headaches I imagine in any distributed system is making sure the work is balanced, right? Here's where it gets really interesting. The goal is to make sure every node pulls its fair share of the weight, so you don't have 9 out of 10 nodes just sitting there, basically idle, while one poor machine gets completely hammered. What's the term for that imbalance?
That's exactly what we call skew, or in the worst case, a hot spot. It's just like a traffic bottleneck, you know?
Yeah.
All the cars trying to funnel into one lane. It slows everything down. Your entire system basically becomes only as fast as its most overloaded part.
Right, the slowest link in the chain. And it's probably worth remembering, partitioning and replication usually go hand in hand, don't they?
Absolutely. They solve different problems but work together. So while any given piece of data, like a user record, belongs to exactly one partition, that specific partition itself might be copied or replicated onto several different machines. That's for fault tolerance, for safety. So a single physical machine, a node, it can be the leader, the main copy for some partitions, and just a follower, a backup copy for others. It gives you both distribution and redundancy.
Okay, so if the main idea is breaking up the data, how do you actually decide which records go onto which machine, onto which node? Let's maybe keep it simple for now. Assume like a basic key value data model where you're always looking up a record using its main ID, its primary key.
Sure. One common method is partitioning by key range. Here, you basically assign a continuous block of keys to each partition. It's pretty intuitive, kind of like volumes in a printed encyclopedia. You know, AB in volume 1, CD in volume 2, and so on.
Okay, so if I know the key, I know exactly which volume or partition it's in.
Exactly. And a big advantage here is that within each partition, the keys are kept in sorted order. That makes what we call range scans super efficient. For instance, if your keys are timestamps, maybe from sensors, you could easily grab all the readings from, say, last Tuesday just by querying the single partition that holds that date range.
That key range approach sounds really elegant, especially for those lookups and range scans, but
Yeah.
I feel like there might be a catch. Does it ever hit limits or cause unexpected issues when things really scale up?
Oh, absolutely. You hit the nail on the head. The big downside, and it's kind of surprising at first, is the risk of creating exactly those hotspots we talked about.
Mm-hmm.
Think about that timestamp example again. If your key is the timestamp, then all the new data, right, all the incoming writes for right now, they're all going to target the single partition that covers the current time range.
Huh. So one partition gets hammered constantly while the older ones are quiet.
Precisely. That one partition gets totally overloaded with writes, while all the others holding older data are basically idle. And that catch really highlights a core engineering insight. Sometimes the simplest seeming approach on paper creates the biggest performance bottlenecks when you deploy it at scale. It really forces designers to think, well, almost counterintuitively sometimes.
So how do people work around that?
Well, applications often have to get clever. For example, instead of just using the timestamp as the key, they might prefix it with something else that varies, like maybe the sensor ID or the user ID. So sensor ANM stamp, sensor D timestamp. That helps spread the current writes across different partitions.
Okay, that makes sense. So to specifically fight those predictable hotspots from key ranges, many systems use a different strategy. Partitioning by hash of key. How does that one work?
Right. So instead of using the key directly to decide the partition, you first run the key through a hash function. A hash function basically takes any input key and spits out a number, often one that looks pretty random. The key thing is even keys that are very similar, like user123 and user124, will usually produce wildly different hash numbers. And that resulting hash number is what's used to assign the key to a partition, usually using some kind of modulo operation or range mapping based on the hash.
And the hash function itself, does it need to be super secure, like for passwords?
No, not usually. It doesn't need to be cryptographically strong. Speed and good distribution are more important here. So you'll see things like MD5 being used, like in MongoDB or Murmur3, which Cassandra uses. They're fast and spread keys out really well. But one important note, you generally can't use the built-in hash functions from programming languages, like Java's object.hash code, because they aren't always guaranteed to produce the same hash value for the same key across different runs or different machines, or even different processes on the same machine. For partitioning to work reliably, the hash for any given key absolutely must be deterministic and identical everywhere, every time. Otherwise, you wouldn't be able to find your data consistently.
Gotcha. So that uniform distribution from hashing sounds incredibly useful for spreading the load. What's the main advantage it gives you?
The big benefit is simply that it's fantastic at distributing keys, and therefore the query load very evenly across all the partitions. It tends to make the boundaries between partitions much more, well, uniformly loaded compared to key range, which helps prevent those hotspots caused by sequential keys or access patterns.
Okay, but my gut feeling says that if you're scattering keys seemingly randomly based on a hash, you must be giving something up, right? Like
Yeah.
maybe that nice sorted order we had with key ranges.
Exactly right. That's the big trade-off. That's the cost you pay for the even distribution. You completely lose the ability to do efficient range queries based on the primary key. If you want to find all items between key X and key Y, you can't just go to one or two partitions anymore. Because hashing scattered them everywhere, you typically have to broadcast your query to all the partitions, wait for them all to search their local data, and then gather all the results back and combine them.
Scatter gathers?
Scatter gather, precisely. And that can be really inefficient, especially as the number of partitions grows.
Okay. And you mentioned hashing. I sometimes hear the term consistent hashing thrown around. Is that related or is it something different?
Good question. Consistent hashing is a term that honestly causes a lot of confusion in the database world. It often gets used inaccurately. It primarily refers to a specific algorithm for rebalancing partitions when nodes are added or removed, aiming to minimize data movement. It's not about ACID consistency or replica consistency. And in practice, true consistent hashing algorithms, like the chord method, are rarely used effectively for data placement in most modern databases. It's generally clearer and less confusing to just stick with the term hash partitioning when talking about how data is assigned based on a hash.
Got it. Hash partitioning it is.
Now, some systems try to get the best of both worlds. Cassandra, for example, offers a pretty clever compromise using what they call a compound primary key. With this, only the first part of the compound key is actually hashed to determine the partition. But then, the other columns in that compound key are used to sort the data within that specific partition.
Oh, interesting. So you get the distribution from hashing the first part?
Right. But you still get efficient range scans if you fix that first part of the key in your query. For example, you could have a key like user read update timestamp. You hash the user id to find the right partition, but within that partition, all updates for that user are sorted by timestamp. So you can efficiently query all updates for user X since last Tuesday, even though different users are spread across different partitions. It's quite an elegant data model for handling common one-to-many relationships.
Okay, but what if you run into a really, really extreme hotspot? I mean, not just lots of writes to a range of keys, but like millions of writes hitting the exact same key all at once. Think maybe a celebrity's single social media post that just explodes with comments instantly. Hashing that single post ID won't help spread the load, will it? Its hash is always the same.
Yeah, that's the nightmare scenario, the super hotspot. And you're right, simple hashing doesn't solve that because all requests for that one key will hash to the same value and thus target the same partition. And honestly, most distributed database systems today don't automatically compensate for those extreme single key hotspots. It usually falls back onto the application layer to handle it.
So what can the application do?
Well, a common technique is to artificially split the hot key. You could, for example, append a random suffix, maybe a small random number like 00 to 99, to the end of that really hot key before writing. So instead of writing to post 123, you'd write to post 12307 or post 12351. This effectively turns that one super hot key into, say, 100 different keys. Since these now have different suffixes, their hashes will likely be different, distributing the write load across potentially 100 different partitions.
Ah, okay, that sounds clever for writes, but what about reads?
That's the trade-off. While it solves the write bottleneck, reading becomes more complicated. To get all the comments for post 123, you now have to query for all the possible suffix keys post 12300, post 12301, all the way to post 12399, and then combine the results in your application. Plus, you add bookkeeping overhead. You probably only want to apply this random suffixing to the keys you know are extremely hot, not to every single key in your database. So the application needs logic to identify and manage these hot keys. It's a classic case of solving one problem, but introducing a different kind of complexity.
Right. So, okay, we've talked a lot about primary keys, the main ID used to find data, but what about searching on other fields? Using secondary indexes, like finding all the cars that are read in a product database, or maybe finding all the news articles that mention the word hogwash. These searches are crucial, right? But they don't seem to map neatly onto the primary key partitioning schemes we've discussed. This feels like a whole new puzzle.
You're absolutely right. Secondary indexes introduce a completely different set of challenges in a partitioned world. There are basically two main ways databases approach this. The first is what we call document partitioned indexes, sometimes called local indexes. The idea here is pretty simple. Each partition maintains its own separate secondary index. And that index only covers the documents, the records, that are stored physically within that specific partition. It has zero knowledge about data living in any other partition.
Okay, so with these local document partition indexes, writes seem like they'd be pretty straightforward. If I update a document, I just update the index on the same partition. Does that simplicity come with a hidden cost somewhere else?
It does, yeah. You've got the benefit right. When you add or update a document, the change only needs to happen in one place. The partition holding the document also updates its local secondary index. So writes involving secondary indexes tend to be quite fast and simple with this approach. The downside, and this is the big practical impact, comes during reads. Let's say you want to find all the red cars, since each partition only knows about its own cars.
Ah, you have to ask every single partition.
Exactly. You have to send that query, find red cars, to every single partition in your cluster. Then you have to wait for all of them to respond with their local results, and finally your application or a coordinator node has to gather all those results and combine them.
That's scatter-gather again.
It is. And it's particularly prone to something called tail latency amplification. Basically, your overall query time is determined by the slowest partition to respond. If just one partition is slow or overloaded, your whole query gets delayed. This local index approach is quite common. You see it in systems like MongoDB, React, Cassandra, Elasticsearch, SoulCloud. Many of them essentially use this strategy.
So the vendors using that often recommend trying to design your primary key partitioning so that your common secondary index queries might, hopefully, only hit one partition anyway.
That's often the advice, yeah. If you can structure your primary key cleverly so that, for instance, all cars of a certain make end up on the same partition, then querying for red Fords might only hit one partition, even with local indexes. But that's not always possible or practical.
Okay, so if the local index approach leads to those potentially slow scatter-gather reads, what's the alternative? Is there a way to build secondary indexes that prioritizes faster read performance?
Yes, there is. The alternative is called term-partitioned indexes, often referred to as global indexes. Here, instead of each primary partition having its own little secondary index, you create a single global secondary index that covers the data across all the primary partitions. And crucially, this global index is itself partitioned. But it's partitioned differently, usually based on the term you're indexing, like color.red or word.hogwash, or maybe a hash of that term.
Ooh, okay. So if I'm looking for red, I figure out which partition of the global index holds the term red, and I just query that one partition. That sounds much faster for reading, no more scatter-gather.
Precisely. Reads become highly efficient. A client wanting to find all documents with color. Red only needs to figure out which single partition of the global index is responsible for the term color. Red and query just that one node. Much faster, much less network traffic.
I sense another trade-off coming. If reads are simple, does that mean writes get complicated?
You guessed it. The complexity shifts squarely onto the right path. Writes become significantly more complicated and potentially slower. Think about writing a single document, maybe a car listing. That one document might have multiple terms you want to index: color.red, make, forward, year.2023. With a global term partitioned index, the entries for color.red, make, forward, and year.2023 might live on completely different partitions of the secondary index.
Ah, so one document right now has to touch multiple partitions across the cluster just to update the indexes.
Exactly. And doing that reliably, making sure all those index updates happen autonomously, ideally requires distributed transactions, which are complex and not always supported or performant in distributed databases.
So how do systems handle that in practice?
Often, updates to these global secondary indexes are performed asynchronously. This means when you write a document, the write might return success to you quickly, but the corresponding secondary index updates happen in the background, maybe a short time later.
So there's a window where the index might be slightly out of date.
Correct. There's a potential delay. For example, Amazon DynamoDB, which supports global secondary indexes, mentions that updates are typically reflected within a fraction of a second, but they acknowledge that delays can be longer, especially if there are failures in the system.
Okay, so global indexes give fast reads, but potentially complex asynchronous writes. Local indexes give simple writes, but slower scatter-gather reads. It's a fundamental trade-off.
It really is. You have to choose based on whether your workload is more read-heavy or write-heavy for those secondary attributes. Some systems, like React's search feature, implement global indexes. Oracle's data warehouse products sometimes let you choose between local and global indexing strategies.
Right. So our data is partitioned. We have ways to handle primary and secondary lookups. But databases aren't static, are they? Data grows, query load changes, machines might fail, or you might need to add more capacity. This brings us to a really crucial practical question. What happens when you need to actually grow or shrink your cluster? How do you move all this carefully partitioned data around without causing chaos or taking the whole system offline?
Yeah, this process is generally called rebalancing. It's about moving data and the associated workload from one node in the cluster to another. And there's some key requirements for it to work well. First, obviously after the rebalancing is done, the load should be shared fairly across all the nodes again. Second, and this is critical, the database has to remain fully operational. It needs to keep accepting reads and writes while the rebalancing is happening in the background. Downtime is usually unacceptable. And third, you want to move as little data as possible. Moving data across the network and writing it to disk is expensive, so you want the process to be efficient.
Okay, so minimizing data movement seems key. My first thought, maybe the naive thought, would be something really simple like just use hash key mod n, where n is the number of nodes. Take the hash, divide by the number of nodes, and the remainder tells you the node number. Seems simple. If I add a node, n just changes. But I have a feeling there's a reason this super simple approach isn't the standard.
You're absolutely right to be suspicious. That hashmod n approach seems intuitive, but it actually fails quite spectacularly when you need to rebalance by changing n. Let's take an example. Say your hash key comes out to 1, 2, 3, 4, 5, 6. If you start with n10 nodes, 1, 2, 3, 4, 5, 6, mod 10 is 6. So the key goes on node 6.
Okay.
Now let's say you add a node, so n becomes 11. What's 1, 2, 3, 4, 5, 6 mod 11? It's 3. So that key now has to move from node 6 to node 3.
Right.
And what if you add another node, n12? 1, 2, 3, 4, 5, 6, mod 12 is 0. The key has to move again, this time to node 0.
Ah, so almost every key has to move whenever you add or remove a node.
Exactly. When n changes, the result of mod n changes for most keys. You end up having to shuffle almost your entire dataset across the cluster. That makes rebalancing incredibly disruptive and prohibitively expensive. It's just not practical for any real-world live system.
Okay, so mod n is out. What are the smarter ways databases handle rebalancing then? How do they minimize that data movement?
Well, there are a few main strategies that are much more effective. One very common approach is to use a fixed number of partitions, but create way more partitions than you initially have nodes. So maybe you decide up front your database will have 1,000 partitions, even if you only start with 10 physical nodes. Initially, each node would manage about 100 partitions.
Okay, so you divide the work more finely from the start.
Right. Then, when you add a new node, say node number 11, it doesn't change the total number of partitions. Instead, the new node steals a few partitions from some of the existing 10 nodes until the load is roughly balanced again. Maybe it takes about 9–10 partitions from each of the original nodes.
And the keys themselves don't change which partition they belong to.
Correct. The assignment of a key to its partition, for example, based on its hash landing in a certain range associated with partition 567, never changes. Only entire partitions get moved between nodes. This drastically reduces the amount of data that needs to shuffle around. Systems like React, Elasticsearch, Couchbase, Voldemort, they all use variations of this fixed partition approach.
What's the downside there? Choosing that fixed number up front.
That's the main trade-off, yeah. You have to decide on the total number of partitions when you first set up the database. If you choose too few, each partition might become very large later, making rebalancing slow and maybe limiting how many nodes you can effectively use. If you choose too many, there can be a small amount of overhead for managing each partition. It can be hard to predict the perfect number if your dataset size is going to vary dramatically over the database's lifetime. So another strategy is dynamic partitioning. This is often used by databases that partition by key range, like HBase or RethinkDB, but also by some hash partition ones, like MongoDB since version 2.4. With dynamic partitioning, instead of a fixed number, partitions can actually split when they grow too large, or merge together if they shrink significantly.
Ah, so the number of partitions actually adapts automatically to the amount of data you have. That sounds really flexible.
It is very flexible. It means the system tries to keep individual partition sizes within a manageable range, maybe based on configured size limits, like split when a partition exceeds 1 GB. You don't have to guess the right number of partitions years in advance.
Any catches with that one?
Well, a small potential issue is that when you start with a completely empty database, it typically begins with just a single partition. All the initial writes go to that one partition on one node.
A temporary hotspot right at the start.
Exactly. It creates a temporary bottleneck until that first partition grows large enough to trigger the first split. To work around this, many systems support pre-splitting, where you can tell the database, even when it's empty, to start with an initial set of empty partitions spread across your nodes. And then there's a third approach, kind of a hybrid, used by systems like Cassandra and also libraries like Kedema, which is used for memcached. This involves having a fixed number of partitions, but it's proportional to the number of nodes, say 256 partitions per node.
Okay, so the total number of partitions grows as the cluster grows.
Right. When a new node joins, it doesn't just steal whole existing partitions. Instead, it randomly picks a number of existing partitions across the cluster, tells them to split in half, and then takes ownership of 1/2 of each of those splits. This random splitting usually averages out to give the new node a fair share of the overall data range and load.
Interesting. So lots of different ways to handle the mechanics. Now, given how complex and resource-intensive moving all this data can be, should this rebalancing process be fully automatic? Or is it better to have a human operator, like a sysadmin, trigger and oversee it?
That's a really important operational question, and there's a spectrum of approaches. Fully automatic rebalancing sounds great, convenient, hands-off. But it can also be unpredictable and sometimes even dangerous. Remember, rebalancing isn't free. It consumes network bandwidth, disk I/O, CPU. It involves rerouting requests. If the system triggers a massive rebalance automatically at the wrong time, maybe when the network is already congested or nodes are struggling, it can actually make performance worse.
Oh, I can see that, like kicking a system when it's already down.
Exactly. Even worse, imagine a node is just temporarily slow, maybe due to garbage collection or a brief network hiccup. A fully automatic system might mistakenly think the node is dead or failing and start aggressively rebalancing data away from it. This puts more load on the already struggling node as it tries to serve data be moved off, and more load on the network and other nodes. It can potentially lead to cascading failures. I've definitely seen situations where An overeager automatic rebalancer turned a minor glitch into a major outage because it reacted too quickly and aggressively.
Yikes, okay.
So for that reason, many operators prefer systems where rebalancing requires some level of human intervention, or at least human confirmation. Maybe the system proposes a rebalancing plan, but an operator has to approve it. Or maybe it's triggered manually during a planned maintenance window. It might be a slower process, but having a human in the loop can prevent these kinds of operational surprises and help maintain overall stability. It's often a trade-off between convenience and predictability, or maybe robustness.
That makes a lot of sense. Okay, so let's assume our data is partitioned beautifully, and we even have strategies to rebalance it as things change. Now, the final piece of the puzzle, maybe, if I'm a client, say, my web browser trying to fetch my social media feed, or an application server needing user data, how do I know which specific node in this potentially huge cluster I should talk to? If data for user Alice is on partition 7, and partition 7 currently lives on node 53, how does my application figure that out, especially if partition 7 might move to node 88 during a rebalance? This feels like a classic service discovery challenge in a distributed world.
It absolutely is a service discovery problem. And again, there are a few common patterns for how requests get routed to the correct partition. Approach 1. The client can just connect to any node in the cluster, maybe picked randomly or via a simple load balancer. If that node happens to own the partition for the requested data, great, it handles it. If not, that node knows where the data actually lives and forwards the request internally to the correct node, gets the response, and then sends it back to the original client.
Okay, so the nodes handle the internal routing.
Right. Approach 2. You have a dedicated routing tier. All client requests first hit this specialized service, which acts like a smart, partition-aware load balancer. This router knows the current mapping of partitions to nodes and directs the client's request straight to the right node from the start.
Like a traffic cop for data requests.
Pretty much. And approach 3. The client itself becomes partition-aware. The client library or the application code somehow obtains and caches the mapping of partitions to nodes, and that it connects directly to the appropriate node for each request.
Okay, this makes sense. But the critical piece for all of them seems to be, how do these components, the nodes doing forwarding, the routing tier, or the smart client, how do they actually learn about changes in the partition ownership? You know, when that rebalancing happens and partition 7 moves from node 53 to node 88, keeping that mapping up to date and consistent everywhere sounds really hard.
It is hard. Ensuring consensus about the cluster state is one of the trickiest parts of distributed systems. This is where coordination services often play a vital role. Many distributed data systems think HBase, SolCloud, Kafka, even MongoDB uses its config servers for this, rely on a separate, highly reliable coordination service like Apache Zookeeper. Zookeeper basically acts as the definitive source of truth for the partition-to-node mapping. Nodes register themselves and the partitions they own in Zookeeper. The routing tiers or the smart clients or other nodes subscribe to changes in Zookeeper. When a partition moves during rebalancing, the mapping in Zookeeper gets updated, and Zookeeper reliably notifies everyone who's subscribed about the change.
So Zookeeper is like the central directory.
Exactly. It provides that consistent view of the cluster topology. Now, some other systems, like Cassandra and React, take a more decentralized approach. They avoid relying on an external service like Zookeeper and instead use gossip protocols. With gossip, nodes communicate changes in the cluster state directly amongst themselves. Node 53 might tell a few neighbors, hey, I just gave partition 7 to node 88, and those neighbors tell their neighbors, and eventually the information propagates throughout the whole cluster.
That sounds complex to implement reliably.
It definitely adds complexity to the database nodes themselves, as they all have to participate in the gossip protocol correctly. But the advantage is it removes the dependency and potential single point of failure or bottleneck of an external coordination service.
And regardless of routing tiers or gossip, clients still need to find some initial IP address to connect to, right? Which is often just handled by DNS.
Yeah, exactly. There's usually some initial discovery mechanism, often DNS, to find the entry point, whether that's a router IP or just one of the database nodes. And just as a quick side note, while we focus mainly on key value lookups and simpler queries, it's worth mentioning massively parallel processing, or MPP, relational databases. These are often used for data warehousing. They have really sophisticated query optimizers that can take a complex SQL query, break it down into many smaller pieces, and execute those pieces in parallel across dozens or hundreds of nodes, each working on its local partition of the data. It's a very specialized form of parallel execution across partitions, crucial for analytics on huge data sets.
Wow, okay. So Stepping back, you've really taken us on a deep dive here into, well, the fascinating world of database partitioning. We've seen how databases have to actually break up data, not just make copies of it, to handle truly immense scale. You understand now the fundamental trade-offs, like between sorting data using key ranges versus scattering it with hashing, and how finding data via secondary indexes presents its own complex puzzle, forcing choices between scattered gather reads or dealing with asynchronous updates.
Yeah, and we explored why rebalancing is so essential for keeping these systems elastic and balanced as they grow or shrink, looking at the pitfalls of simple approaches like mod-n and the smarter strategies involving fixed partitions, dynamic splitting, or proportional assignment. Plus, the different ways requests get routed to the right place, whether through forwarding, dedicated routers, or smart clients, often relying on coordination services like Zookeeper or decentralized gossip protocols. The core theme through all of this, really, is that each partition aims to operate largely independently. And it's that independence, that ability for each piece to work on its own slice, that fundamentally allows the database to scale out across many, many machines.
Right. And while that independence is definitely the key to achieving massive scalability, it does raise one more really interesting question for you, the listener, to maybe ponder. What happens when a single operation, maybe even a single write request, needs to touch data across several different partitions at the same time? What if part of that operation succeeds on one partition, but another part fails on a different partition? How do you maintain consistency then? That sounds like a whole other can of worms. Or perhaps a whole other deep dive for another time. Thanks for joining us on the deep dive.